All right, welcome everybody to chapter 12. We have 2 more chapters to go. I hope that you enjoyed Graham's guest lecture last time, lecture 11. Today we're going to talk about lazy evaluation. Lazy evaluation is very special to Haskell. There's not any other functional language that I know of that's popular that has lazy evaluation, so let's jump right in and look at an example of where we're using different orders of evaluation and then look at the differences. In the example that you see here, we have a simple function increment. Increment by now should look familiar. Increment of n is just an alias for n plus 1. And the type of this is int to int. Now, if we have an expression that involves inc, let's say inc 2 plus 3 or times 3, I think that's what we have on the slide. Now there's multiple ways that we can go and evaluate this expression. And if you look at this expression here, there's 2 places where there's what we call a redex, a reducible expression. That's something that we can evaluate. And the 2 places are this expression here, 2 times 3, we can evaluate that to 6, or we can use the definition of inc and replace this whole call, let me underline that, if we replace the whole call by unfolding the definition and then continue. And if you look at the slide, I have underlined these redexes, and on the left you see that we're always reducing the innermost redex. That means that's a redex that doesn't contain any nested ones. So in that case, when you have inc 2 times 3, you first have to execute 2 times 3, and then we get inc of 6. Now we execute inc of 6 by unfolding, so we get 6 plus 1, and that reduces to 7. On the right hand side, the right column there, we're going to do the opposite. So what we're doing is we're going to reduce the outermost redex. So that's a redex that is not nested itself inside another one. And in this case we have inc of 2 times 3, that's the outermost one. So what we'll do is we'll unfold the definition of inc and substitute 2 times 3 for the argument n. So what we get is we get now 2 times 3 plus 1. Now we execute 2 times 3, 6, and then I forgot to underline it here. So 6 plus 1 becomes 7. So what you see here is that the order of evaluation didn't matter for the end result. I evaluated both of these expressions in a completely different order, but in the end both of the execution orders returned 7. Now let's look at the same program in Pigeon C#. Let me write the code here on the whiteboard. So we start here with a variable var n equals 0. And what we're going to do is we're going to execute this assignment here. M equals n plus n becomes 0. And here I'm using assignment as an expression that as a side effect assigns 0, and I should write a correct example, that assigns the value 1 here to n and then returns 1. So it's a side effecting expression. And now when you have side effects, the order of evaluation becomes important. Let's evaluate this expression in 2 ways. So the first one, I'm going to execute this assignment first. So the effect of that is that n, whose value used to be 0, becomes 1. The whole result of this assignment is 1. So now we have 1 here. Well, I've assigned n to 1, so this becomes 1 plus 1. So the result is 2. That's what you see on the left column. If, on the other hand, I first execute the left-hand side of the addition there. Well, in that case, n is still 0 because it was initialized with 0. So we get 0 here, and then we assign n to 1. So we get 0 plus 1, and the result is 1. So if we execute this one first, the assignment first, the result is 2. If we execute the assignment second, the result is 1. So here you see with impure, when you have side effects, you can observe the order of evaluation. The way you execute your expressions will have a noticeable result, effect on the result. Let's look at a slightly more complex example. And as you see, we have a little change of scenery here. You know, like now there's like 3 big pieces of concrete. And now I can store my wiper there. Let's look at this next example. Instead of addition, we're doing multiplication. So we're defining the function mult with pattern matching. So it takes a pair x and y, and it just multiplies the 2. And I'm going to execute this expression mult of 1 plus 2 and 2 plus 3. And again, I can do this in different orders. For example, if I look at the kind of leftmost, outermost, the leftmost, innermost redex, then I get this guy. So this is something that's a redex. I can execute that, I can simplify it, and there's nothing nested inside it. So what I will do is I'll execute that one and replace the value by 3. Now I'm looking for the other thing that doesn't have any nested redexes. So that's 2 plus 3. That's 5. Now there's no nested one, so I have to execute this one. So I use the definition. So this thing is rewritten to 3 times 5. And now I get this redex and I replace that by 15. So here in this case, I've done innermost evaluation. I kept reducing the most nested redex. Let's do the outermost execution. And that's what you see on the slide on the right hand side. So let's write down that expression again. I multiply 1 plus 2 and 2 plus 3. Well, if I take the outermost one, well, it must be this one, because there's no redex outside of this. So what I do is I have to instantiate x with 1 plus 2 and y with 2 plus 3. I'm going to cheat a little bit here, just doing it like this. And now I'm ending up with this expression. And since multiplication requires that its arguments are evaluated, I have to evaluate that guy. So now I'm going here to 3. I have to execute that guy. It's 5. And again, surprise, surprise, I end up with 15. In that case, I've used outermost evaluation. Outermost evaluation is sometimes called call by name, because what you do is whenever you're applying a function, you're not evaluating the arguments, you're just taking the expression that represents the arguments and filling that in for the argument. And the other one is called call by value, because when I'm evaluating that function like mult, I first evaluate the arguments completely and then substitute them for the result. And so here are these things that I kind of put side by side, and they are dual, because one uses the innermost. They always looked for the one where there's no redex nested inside, and the outermost execution order was the opposite, where we took anything that didn't have a redex outside. This notion of duality is a very interesting one. For those of you that have followed the RX work, that we just released on DevLabs and all the other videos on Channel 9, RX is also all based on duality. And duality, as I've said before in other videos, really appeals to me because it gets you kind of, buy one, get one free. And it's often a very, very powerful mechanism to learn more about the topic that you're studying. And then the other thing that I showed you was strictness. The multiplication here is strict because I can only apply or reduce the multiplication if both arguments are fully evaluated. If they're still expressions, I cannot do that unless I go to a system where I can do symbolic execution, but that's not the case in Haskell. So in Haskell, when you have a multiplication, both arguments must be fully evaluated. Now this notion of independence of evaluation order has a very nice theory behind it. And one of the main theorems is the so-called Church-Rosser theorem. This theorem was proved in 1936 by Alonzo Church and Barclay Rosser. Church, the guy that invented the lambda calculus. I have here on display Henk Barendrecht's book on the lambda calculus. This is sometimes called the Bible of the lambda calculus. And it contains a nice proof also of the Church-Rosser theorem and all kind of other goodies. So if you're really kind of into functional programming, this would be a nice Christmas gift for you. This yellow book. And plus, I think it just looks good in your bookshelf, on your bookshelf. But the idea of the Church-Rosser theorem is that if you can, draw the picture here, is that if you start with an expression, some term, let's call that A, and if I reduce that in two different directions, for example, in this case I did outermost reduction, and in that case I did innermost reduction here, and I get at two terms B and C, what this theorem says is that you can always find there must be some D such that I can now reduce B and C both to D. And this is a very powerful thing because it says that it doesn't matter in what order you evaluate things, because in the end I always get at the same value. So the end result of my computation is independent of the evaluation order. And this is what allows a pure functional language, or any language for which this Church-Rosser theorem holds, to introduce parallelism. The fact that I can reduce these things in arbitrary order, that's the beauty, because now the execution machinery can pick its evaluation order, and you don't have to worry that, like in the imperative example that I showed, that you end up with a different result. The Church-Rosser theorem, very, very important and beautiful theorem about functional programming. Now let's look at the same mult example that we had, but instead of writing that with a pair, let's write it as a lambda expression. Okay, so write it down here, mult. So instead of writing xy equals x times y, I'm going to write it in curried form. So I'm writing mult equals lambda x, lambda y, x times y. And now I'm going to execute that. So I'm going to execute mult again with 1 plus 2 and 2 plus 3. And in this case, let's look at the slides. I'm going to execute the leftmost innermost radix. So in this case, that's this guy, that's the leftmost, there's no nested ones here. So I'm going to evaluate this thing to 3. And now, unlike in the other case, I'm not going to execute this one because there's another leftmost redex that has no inner redexes, namely the partial application of multiplication to 3. Because in this case, I've defined this as a lambda expression. So what I do now is I'm applying this thing here, and what I get now is the following application. I get lambda y, and this was 1 plus 2, that's 3 times y applied to 2 plus 3. And now I have to execute this guy. It's 5. And now I can substitute that in there. And so I get 3 times 5, which is 15. Okay, so the interesting thing here is that the partial application was done before the other argument. Now, lambda expressions are interesting in other situations too, when you look at evaluation, namely that normally Haskell doesn't evaluate anything below a lambda. So if you have the example here that's on the slide, a lambda x 1 plus 2, if I apply that to 0, we don't consider the 1 plus 2 under the lambda as a regex, because we're not looking under the lambda. This function is considered as a black box. Only when I apply it to an argument, and in this case, since x is not used in the body, the 0 just disappeared, then I can start executing the body, but not when it's under the lambda. And in this case, this just returns to 3. Notice that if I would execute under the lambda, that would be fine too, because, you know, in that case, the body of the lambda would be reduced to 1 plus 2. I would have lambda x 3, apply that to 0, and that would be 3 too. But Haskell considers lambda expressions to be values, and so it doesn't execute underneath. Now let's look at the differences in behavior between these two forms of evaluation, call by value and call by name. And let's in particular look at the differences between these two with respect to termination. And for that, we're defining this crazy function here. Crazy function that creates an infinite number. And so what do? I just add 1 to itself infinitely many times. So I say inf equals 1 plus inf. So this is a recursive function. And let's use that. Let's look at the expression first of the pair with 0 and inf. Now if I do call by value, I have to execute here all the kind of, innermost redexes. So in that case, I have to execute this guy. And what I have to do then is to unfold its body. So this becomes 1 plus inf. Well, and now I see another redex here, namely inf again. So this becomes 1 plus inf. And not to bore you, I will stop here because, obviously this thing goes on forever. So when you do call by value and you have this kind of runaway recursive functions, you might run into non-termination. And that's perfectly okay, but it's caused by the fact that I'm kind of too eager here to execute that argument, because if I would do call by name, in that case, well, since first ignores its second argument, this would just go to 0. And there's no need at all to even touch that argument. So the lesson here is that call by name terminates more often than call by value. Why is that? Because, if the function does not use an argument, in call by name that argument will just vanish, won't even be evaluated ever. Whereas if you do call by value, that argument will be executed even though it's not needed, and that might run away. The recursion might run away. Now let's look at efficiency, the number of steps it takes to reduce an expression. And there, call by value does better in this example. What we're going to do here is we're going to duplicate the argument. So we're defining the function square square of n as n times n. And what we're going to execute is a square of 1, what do we have here, 1 plus 2. Okay. Under call by value, we're going to execute this one first because that's the innermost regex. So we're replacing this by 3. And now we're unfolding the definition, and it becomes 3 times 3, and then we can execute that one, and it becomes 9. All right? Fairly simple. That's what you see here on the left-hand side of the execution. Now, if we instead use call by name, it looks a little bit different, because in that case, if I do 1 plus 2, now I have to evaluate the outermost regex, which means that I have to call by name, I have to just substitute this expression for the argument. So now the expression 1 plus 2, instead of getting evaluated to 3 and substituted here, it is evaluated or substituted literally, and now I'm duplicating that work of adding 1 plus 2. So this goes to 1 plus 2 times 1 plus 2. Oops. Okay, and so you see that it's more work because now I have to perform this addition twice. I've duplicated the work because I've substituted the argument so-called by name. So in general, call by name may require more steps than call by value in case that argument is duplicated and used. Of course, if I would have defined square to be like this, in that case, call by name would have used less steps because I would immediately just replace this guy by 4, 7, 11, whereas if I would use call by value, I would execute that one needlessly to 3 just to throw it away. So call by value in certain cases is more efficient. It takes less steps than call by name, but definitely not always. So now the question is, can we combine the best of call by name with the best of call by value? And the best, I mean that it terminates as often as call by name and that it uses as few steps as call by value. Now, what is the trick that we need to use? Well, apparently when we do call by value, when an argument is used twice, it's executed only once. Now, in order to achieve that, we don't really need to execute that argument eagerly. We don't have to execute that up front. What we can do is we can share the execution of that argument. And if we can do that, then we can still defer the execution. But once we've evaluated that n here, I should put my example back. If we could share the evaluation of n, then we get the best of both worlds. And that is what lazy evaluation does. Lazy evaluation is call by name plus sharing. And if you look in the book, by now I hope that everybody has a copy of the book. If you go to chapter 12, I don't know if this is visible, but on page 130, you see that this uses like some fancy notation, like a graph-like notation to do the sharing. On the slide here, I used a let notation to achieve the same thing. So let's look at how this evaluates when we're using lazy evaluation, call by name plus sharing. When we're executing square 1 plus 2, we do the same as we did before. We're not executing that argument 1 plus 2 up front, but we're also not substituting that for every instance of n. Instead, what we do is we use a let binding. We say let n equals 1 plus 2 in n times n. And now when we execute the first n, the first occurrence of n, we're updating the let binding. So let n equals 1 plus 2, we execute that to 3, and now by doing that, every occurrence of n will be evaluated. So in one step, we have evaluated, in some sense, both of the arguments of the multiplication, and then we can just multiply that and we end up at 9. So here you see that we get exactly the same effect of call by value, the sharing of call by value, without having to do that up front. And we do that by sharing all the occurrences of that argument appearance in the body. And lazy evaluation gives you the best of both worlds. It terminates more often than call by value, and it never requires more steps. So that's a very beautiful property. Now, of course, there's still, it's not kind of really true what we say here is that it requires more steps. There's still more overhead, right? Because we still have to build this sharing and so on. So in certain cases, in this case, if you know that you're going to evaluate the argument and that you're going to need it in any case, making it strict is more efficient. And this is what the Haskell compiler tries to do. It tries to analyze your functions and see if it can use call by value instead of lazy evaluation, such that it can prevent the use of all the overhead of introducing the sharing and updating the let binding, etc., etc. But in general, I think this is a beautiful thing that you share all the computations of that argument. And notice, if you go back to our previous example, the fact that we can share this expression here, 1 plus 2, relies on the fact that the order of evaluation doesn't matter, because we don't know when things get evaluated. We can do it up front, doing call by value, or we can share the thing, or we can duplicate the execution. In the end, this expression always will return 9. So to give the execution engine of the functional language most freedom to reorder the expressions, we have to be pure, or in other words, the Church-Rosser theorem should hold. Now let's look at some examples of infinite structures, like the infinite number, like inf equals 1 plus inf that we've shown in the beginning. But in this case, one that's maybe more useful, or actually it is quite useful, the infinite list of ones. And we can write that one using a recursive function as follows. We can write ones equals 1 cons ones. And if we evaluate that on the left-hand side on the slide here, you see that we replace ones by its right-hand side. And then we can take the ones there, here, and replace that again by its definition. And if we just keep on doing that, we'll see that we get an infinite list of ones. Now the nice thing is that if you use lazy evaluation, when you take head of ones, the pattern matching, because head is defined using pattern matching, will force the execution of ones just one step far enough such that head can perform its pattern matching. So it has to kind of reduce one step to become 1 cons ones, and then head can proceed and just return 1. And so that's the property of lazy evaluation, that it only evaluates the arguments when it's strictly necessary, and then also it shares the result, so it never duplicates the work. So that's a very powerful execution mechanism. Now, I mentioned this paper before, Why Functional Programming Matters by John Hughes. That's all about why lazy evaluation is useful in composing programs. And here I'm giving you a very, very simple example where we're defining the function take function take that takes a number and just grabs the first n elements from a list. And it's defined by case analysis over the both arguments. So if I take 0 elements from a list, well, that's the empty list. If I take whatever elements from an empty list, well, I return the empty list as well. And now you see that I'm using, in the third case, simultaneous induction. If I take n plus 1 elements from a list, that starts with x and the rest is x's. What I do is I take x and I const that in front of the list where I take n elements from the remaining list. The beauty of lazy evaluation is that I can apply this function to both finite and infinite lists. It doesn't matter because this function here will just evaluate its arguments enough to take the first n elements. And it doesn't matter if that whole list is infinite. Whereas if you do eager evaluation, you have to, well, you can see here already that that's very wasteful, because it will evaluate its list argument completely, even though, and say that it's not an infinite list, but it's like a million elements. So what it will do is it will create a million element list only then to take the first n, say that n is 5, to take the first 5 elements. And this is what John Hughes says makes lazy evaluation compositional, because I can take a function that produces a list without knowing where that function will be consumed, whether that function will be consumed by take or by anything else. And if it's not compositional, I have to be really careful if it's eager evaluation, because now I probably don't want to produce that list and then take it. So I have to kind of define these functions together. And I cannot define my functions as separate pieces and then stick them together. No, I have to look at my program as a whole and make sure that I don't execute things that I don't need to. And I really recommend you to read John's paper. Now, it's not all motherhood and apple pie with lazy evaluation. You have to be careful. Let's look at a couple of examples here. If I take 3 from the infinite list of ones, that works fine. I just get the list with 3 ones by unfolding the definition here 3 times. Remember the function filter from, I don't know, that was like chapter 1 or 2. Filter takes a list and a predicate, and it throws away all the elements from the list for which that predicate is not true. Now I'm applying the predicate here less than equal to 5 to the infinite list 1, 2, 3, etc. What this will do is it will take the first 5 elements, but then, and I've used the symbol bottom here on the slide, then it will loop forever trying to find elements that are less than 5. Okay, so that will not terminate. So what you get is you get this list that after its 5th element will have like an infinite computation that is not terminating. But again, since it's lazy, if I take 2 of this filter less than 5, that will work fine, as long as I'm not accessing anything beyond that 5th element there, everything is fine. Now if you look at the third example where I do take while less than 5 of this infinite list, that one creates a terminating list because after the predicate has turned false, that take while will terminate. So you have to be a little bit careful with lazy evaluation. On the other hand, I must say the fact that I can have a list like the one here in the middle that has a couple of elements and then the rest of the list is some non-terminating computation, I think that's quite beautiful too. Because as long as I'm not touching that non-terminating part, everything is fine. And the final example in this chapter here, chapter 12, is primes. We've seen in an earlier chapter how to find prime numbers, but that example generated a finite list of primes. And since we're talking here about lazy valuation, let's see if we can generate an infinite list of primes. And the algorithm is pretty simple. I don't dare to call this Aristosthenes sieve anymore. There's a very nice paper if you search for prime sieves that says that, you know, this is not really according to our Greek philosopher. You should read that paper. But the algorithm is pretty simple that we're going to use here. And it works as follows. We start with the infinite list of numbers starting with 2. That's what you see here on the top line. 2, 3, 5, 4, 5, etc. And we say, let's take the first number in that list must be prime, because it's not divisible by any other number. And then what we do is we're going through the rest of the list and filter out all multiples of that first number. Because that's the idea. These are all then divisible by that first number. When we do that for 2, you see that we are crossing out all the even numbers, and now we get a new list. Okay? The new list in which all the duplicates of 2 have been removed. Now the first element of that new list must be a prime number, because it was not divisible by any lower numbers. So then what we will do is we'll cross out all the multiples of that new prime, in this case 3, so we will kick out, well 6 was already kicked out because it's a multiple of 2, so we'll kick out 9, etc. And then we go and repeat that with the list below that. So that one is 5, so we'll kick out all the multiples of 5, etc. So we're repeating that. So this simple algorithm is really easy to transcribe in Haskell. And here's the code. We say sieve of the infinite list starting at 2. And what is that sieve thing? Well, that's exactly what we said, is we look at this list, we take the first number as the prime number, and then what we do is we recursively apply sieve to the list where we throw out all the numbers that are divisible by the prime number. And I've used list comprehensions here and the explicit filter function. But you see here that the algorithm and the description here are extremely close. And I'm here kind of executing on an infinite list of values to create another infinite list of things. And it's very interesting if you play around with this a little bit and write down the execution where you see that there's now multiple sieves kind of nested within each other that each filter out multiples of their numbers. All right. Now, in Haskell, everything is lazy by default. And we've seen that sometimes things are strict, like the function mult x comma y equals x times y. And we know no matter how I call this function mult here, x and y at some point must be fully evaluated, because that's what multiplication requires. Now the Haskell compiler can do that for you by strictness analysis, or you can specify it yourself. And for that, Haskell has this special operator, strict application, and strict application forces the execution of its argument. So if I apply f to something that doesn't terminate, the whole application won't terminate. And otherwise, if I apply f to x, it will be the same as f of x. This is a pseudo function because obviously in real life I cannot pattern match on bottom, but this is the behavior of this function. And you can use this in certain patterns. If I want to, if I have a binary function and I want to force the evaluation of the first argument, I write f $bang x applied to y, and looking at this definition, this will force the first argument to be evaluated. If I want to force the evaluation of the second argument, then I just write f of x $bang applied to y. F of x, since f is a curried function, will just evaluate to a function that still waits for its second argument. It will force the evaluation of that second argument and then apply the function. And if I want to execute both of them, I write the expression below here on the third row, f $bang x in parens applied to not $1, of course, that should be a $bang. There you see that I forgot to use the shift key. Okay, our final example will be to use this strict evaluation to increase performance. Let's look at this example here. I want to sum the elements of a list, but I want to start with a particular value. I want to start with some value v. The function is defined here by induction over the list. If I want to sum a list starting with v, well, if the list is empty, I return v. And otherwise, what I do is I recursively sum the list and I add the first element of that list to my local variable v. And the idea here is that I'm simulating a loop. I'm making this till recursive function where that v plays the role of a local variable, and I'm just kind of iterating over that list, adding the value to my accumulator. Unfortunately, because of lazy evaluation, this function doesn't really behave the way you think it behaves. Because what it does, it will just go and execute, and if you see here, at some point it will end up with the empty list, and instead of having the actual sum of all the values, it just has a big unevaluated application of additions waiting there until you say sum width of the empty list, and then, only then, that big addition will be executed. And I would argue in most cases that is not what you intended to do. What you just wanted to do is to keep a little counter to count to sum up the elements of that list. You didn't want to build this unevaluated big expression of additions. And to solve that, what you do is you simply use this strict application. So you say when it's empty, I just return v, and in the other case, I'm making a recursive call, but before I make the recursive call, I want to execute that addition. And you use that with the $bang. And then what happens is that you don't get that big expression, but every time the next element is added to that accumulator, the result will be computed. So you force evaluation before the recursive call. Now, as an imperative programmer, it's kind of funny that we had to go and jump through so many hoops to write an efficient version of just summing up the elements of a list, because in C#, you just write this loop, you do a for each, and you just have your local variable. You don't even have to declare a local variable, you just reuse the argument, you add it up, and you return the thing. The code is not that much longer, but it's kind of efficient to start with. So there's kind of your trade-offs between having lazy evaluation and having eager evaluation. If you look at a language like F#, where evaluation is strict by default, but sometimes when you want to do lazy evaluation, you can use it. So there's a way to make a computation lazy. just like in Haskell, where there's an explicit way to make a computation strict. And in .NET 4.0 in the PFX library, there's also support for making computations lazy. Often that's done with lazy initialization. When you create an object, you don't want to kind of do work until the first time that somebody accesses a field or something, and then you want to do some expensive computation, and you also want to do it once. So you see that there's a cross-fertilization of lazy evaluation is useful in an eager context, and eager evaluation is useful in a lazy context, and people want to tweak. Personally, if you ask me, I'm not so sure which one I like. I kind of like both. Sometimes when I'm doing programming like this in C#, I don't really, you don't really want to have lazy evaluation by default. The reason is that when you have side effects, you want to be very precise about the order of evaluation, in which case you want to do strict evaluation, because then you know exactly when things are going to happen. If you don't have side effects and you're in a pure world, then lazy evaluation is great, because then you just leave it to the compiler or to the runtime to figure out how to execute things. And I think it's good to have the two worlds kind of side by side, and that in each world you can kind of pick and choose what you want. But I think the defaults are good. If you're in an imperative world with side effects, you want to do eager evaluation. If you're in a pure world, you want to have lazy evaluation and make strictness explicit. And the reason is that you get all that modularity from lazy evaluation. All right, that was chapter 12. Again, take a look at this book. Of course, buy your copy of Programming in Haskell, and see you next time in chapter 13, where we're going to talk a little bit more about equational reasoning that we have already done here, but we're going to take that up to the next level. So thank you very much, and see you next week for chapter 13.